We start admitting everyone now. Okay. Hello, everyone. My name is Emmanuel Bimpo Manfo. I'm from Jodrell Center for Astrophysics and the Jodrell Observatory at the University of Manchester, UK. And I'm delighted to welcome you all on behalf of the organizing committee to this series of online seminars, which is sponsored by the European VLBI network, focusing mainly on high-resolution radio astronomy. Before we start, I would like to mention a few logistics just for us to be aware and keep note of. First, you will all be muted throughout this presentation, but you will all also be invited to type in your questions that you may have for our speaker, and preferably we would want you to type these questions in the Q&A section of the chat, not as a chat message, but in the Q&A section or facility. At any time during the talk. And also, if you are watching us live on YouTube, please use our YouTube chat to put in your questions. There will be enough time for all your questions right after the talk. So please keep them coming as and when you have them. And we will also ask that you kindly write your questions clearly and keep them short. You can also raise your hand if you want to make the question yourself at the end of the presentation by our speaker. We will aim to get to as many of your questions as we can, and we apologize in advance if for any reason or maybe because of time constraint, we are not able to get to your question. Now, I will ask Anna to introduce our speaker for today, Miguel Pérez-Torres.
Good day, everyone. So it's my pleasure to introduce Miguel Pérez-Torres obtained his degree in physics in 1994 from Moscow State University and his PhD in physics in 1999 from the Universidad de Valencia in Spain. Next, under the prestigious Marie Curie Fellowship, he stayed at the Instituto de Astronomía in Bologna, that was followed by 5 years Ramón y Cajal Fellowship at the Instituto de Astrofísica de Andalucía in Granada. He has developed his career in radio astrophysics there in Granada and obtained a research scientist position in 2009. And he was promoted to senior research scientist 10 years later, a position he currently holds. His research has focused mainly on radio interferometry with 3 main subjects: explosive transients. His pioneering radio studies led to the first radio detection of a type 1A supernova. He works on star formation and nuclear activity in luminous infrared galaxies using VLBI networks, in Merlin, the legacy project LIRGs, and LOFAR. In science paper, he co-authored the first resolved radio jet from a tidal distribution event he was reported. The third topic, ultra-cool dwarfs, brown dwarfs, exoplanets. He has pioneered radio investigation of star-planet magnetic interaction of M-dwarf systems and co-discovered the first radiation belt around a brown dwarf. Also a paper in Science. He collaborated in many national and international projects, supervised several PhD theses. He served as secretary of the Spanish Astronomical Society, evaluated funding requests to the ERC and to Spanish, Polish, French, Belgian, Italian, and Argentinian programs. Miguel is active to science outreach as well, regularly contributing to radio programs, podcasts, and popular astronomy magazines. He practices Pilates, enjoys climbing in the Pyrenees, and is learning to play the keyboard. For me, he's multi-instrument, multi-band, multi-talented person. Enjoy the talk. Miguel, the floor is yours.
Thanks a lot. Thanks for this nice presentation, Anya. And let me just, I hope you can see and hear me well.
Yes.
Okay, perfect. So good morning, everyone. I'm Miguel Pérez-Torres from the Instituto de Astrofísica Andalucía. And I would like to thank the EVN Seminar organizers for giving me the opportunity to present our work. And today we will explore one of the most, I would say, remarkable nearby systems for studying star formation in galaxies, R299. So over more than a decade, this system has revealed itself as a truly extraordinary case. We detected a prolific supernova factory in one of the nuclei. We also detected the long sought AGN there. Finally, we also were surprised by the detection of what happened to be a tidal disruption event in nucleus B1. So that's the story I will tell you about that. And it's remarkable that R299 gives us in just one single system the opportunity to study how star formation, black hole accretion, and stellar death are all intertwined. So before I dive into R299 itself, let me briefly set the stage. So we are talking about LIRGs. R299 is a LIRG, luminous infrared galaxy, and those systems are defined as such by their enormous infrared output, infrared luminosities. So we think that most of this infrared luminosity is powered by massive star formation. Also, in some cases, there is contribution from AGN activity, and they are among the most vigorous star forming systems in the universe, in the local universe. So they are frequently caught, as you can see to the left, in various stages of merging. Those objects play a crucial role in the overall star formation history of the cosmos, and R299 is a textbook example. It is in an intermediate stage merger, very bright in infrared, and is the result of basically the gravitational encounter between two gas-rich galaxies, which fuels intense starburst and possibly black hole accretion, as you will see in a minute. So this slide is just to focus on the understanding of the radio spectrum, the typical radio spectrum of a star-bursting galaxy, such as R299. So this is a key diagnostic for the physical mechanisms that are at play in those environments. Mainly, if we assume that just massive star formation is happening in those starbursts, what we have is that when we have free thermal emission, this is the blue solid line, that dominates above, let's say, 30 gigahertz. Below 30 gigahertz and down to less than 1 gigahertz, the realm of the radio emission is synchrotron radio emission. This synchrotron radio emission is a non-thermal process and comes from the relativistic electrons spiraling along magnetic field lines when those massive stars have exploded as supernova. So they are telling us about the sites of star formation, but at different stages. The final introductory slide is the famous far-infrared to radio correlation, just put here for people that are not familiar with it. So basically, we only have massive stars exploding, a starburst. We have these massive stars that yield copious amounts of UV radiation during their lives. And this UV radiation is reprocessed and re-emitted in the far infrared because there is dust around them. Now, when these massive stars explode as supernovae, we have relativistic electrons diffusing out, and they emit copious amounts of radio emission. So there is naturally a far infrared to radio correlation. Now, on the other hand, if we have an AGN, or both things, a starburst and AGN, the AGN has an accretion disk, and this accretion disk also produces a lot of UV emission re-emitted in the far infrared for the same token. And on the other hand, this AGN has typically a core jet structure. We have seen this many times in the radio, and this produces actually a lot of radio emission. So again, this far infrared to radio correlation appears here. So you see that disentangling which is the powering source is really important, and you will see in a minute how we do this with radio observations. So let me now start with R299, our nearby LIRG laboratory. It is a merger, a nearby merger, 45 megaparsec. It's actually the brightest luminous infrared galaxy within 50 parsec. And it is so bright in the infrared that it is close to being a ULIRG, an ultraluminous infrared galaxy. And correspondingly has a huge amount of star formation, something like 150 solar masses per year, and correspondingly also a high Caucula supernova rate, between 1 and 2 supernovae, Caucula supernovae per year. That's, to compare with our galaxy, we have just one supernova every 50 to 100 years. So these beasts, like R299, are producing orders of magnitude more stars and supernovae than normal galaxies. So they are a perfect laboratory to study this star formation. Let me also mention that most infrared emission comes from this so-called nuclei A and B that corresponds to the two merging galaxies. C and C prime are of nuclear regions of star formation, and this D source marked here in the innermost infrared image is not related at all. So this is a background source. Now let's go into this matrix veil. Why radio is needed? Well, you see here in this image a number of exploding supernovae that have been detected in okay. I think there is someone here with a microphone open. You can see here a few supernovae that have been detected in the optical or even the near infrared. Those supernovae do not correspond, if one takes the Caucula supernova rate out of this, is way below the supernova rate that should have this R299 galaxy. And this is the reason is mainly because those nuclei, those galaxies are dusty buried. I mean, you have a lot of dust to the central regions, and you see that none of these supernovae has been detected close to the nuclei. So of course, there was the suspicion that if we have a high hydrogen column densities, this will prevent the detection of such supernovae. So that's an advantage of radio. We can go when radio is free from extinction effects. It can give us the true estimates of supernova rates, and by combining the Caucula supernova rates with an assumed initial mass function, we can directly measure the star formation rate. So that's a really important tool. Radio observations. So in our work led by our former PhD student, Cristina Romero Cañizales, she used multiple epochs spanning over 11 years, taken with the VLA. You see the system up there in the top panel with a number of supernovae, none of them again close to the nuclei. Now the bottom panels show the radio-like curves for the nuclei A and B, and the nucleus A, the variability wasn't clear, so there was no clear detection of supernovae there. But in nucleus B, these unresolved radio observations allow us to pinpoint a number of bursts. And please pay attention to the to this latest burst, because it will become explained later on in the talk. Now, from these observations, we obtain a lower limit to the Kokkola supernova rate in nucleus B. So even unresolved observations in radio can be useful, can be more useful maybe than in the optical or the near infrared, but this is still not what I will show you in a minute using really high angular resolution radio observations. Before we jump into that, let me also show this nice work led by also our former PhD student Naim Ramirez Olivencia, where she used low-far VLBI observations of our own. They had subarc angular resolution, and they traced very nicely both the ISM and the nuclei, as you can see in this beautiful image. Actually, from this work, she was able to find evidence for a starburst driven outflow in R299A, this elongation. And you are interested, please go to the paper, because I don't have the time to go into details here. We also could estimate the starburst age, kinematic starburst age, being about at most 8 megayears. And also from combining the low-far observations with VLA observations at multiple frequencies, we could trace very well the ISM for the whole system, showing that the spectrum was consistent with the star-forming regions in all those nuclear sites. So that was a very nice work. But now let me explain why do we need VLBI. So in the top panel, you are in those panels we are seeing two different galaxies, two SMN galaxies. And what we see is that as we go from low angular resolution observations with the VLA, which cannot resolve the source, and progressively with higher angular resolution like Merlin, we start to see in the bottom panels some resolved emission. So it's not just one blob, it's, let's say, 2 blobs. And we go to the VLBI, we then start to see what are the really compact sources there. So the upper panel basically is telling us, okay, you are dealing with an AGN. No matter how, the AGN is very small, the black hole, you are not resolving it even with VLBI. However, the lower panels are telling us that because we have completely resolved out the emission, we are actually seeing a starburst region where basically there is no compact object, there is no supernova, it's just the relativistic emission, radio emission, synchrotron radio emission from relativistic electrons diffusing in that region. But this is telling us you are dealing with a starburst region, okay? So now we are moving to the R299A, and the first result of using this high angular resolution observations came with the use of the EVN, the Electronic European VLBI Network. I believe our team was the first to use the EVN for a LIRG, for a luminous infrared galaxy, which was R299. And the bottom panels, the top panel is the VLA image, and the bottom panels basically are showing a rich cluster of compact radio sources in that nuclear region. There is evidence of new objects from comparing the two bottom panels, and the radio emission of those compact sources, most of them, are typical of supernovae. As you can see to the right, this type 2b, type 2l, and type 2p supernovae could be are what we think we saw at the time. These results supported a recent starburst, also in agreement with the results by Naim that I just showed. And that's the way we started a monitoring on this supernova factory, because at that point we were really convinced we were seeing something really interesting, and we were interested in measuring the Kokkola supernova rate. So here in this work, led by my collaborator and friend Marco Bondi, this graph is to illustrate the comparison of compact versus extended radio emission. So what we see is that the contours trace the diffuse emission, the extended emission as imaged by Merlin, whereas the plus signs that you can see there, some of them marked, correspond to locations of the supernova sites. Okay, so basically they trace the same physical region, which is of course not surprising. Actually, the diffuse emission, the extended emission, follows the sites where the supernovae are exploding, because it is the radio emission from these regions that is going to be diffused out through the whole system. So eventually, from these regions here, we will see radio emission diffusing out, like these contours. Let me also mention that the compact radio emission is just 10% of the whole radio emission. So most of the radio emission is in the form of diffuse emission, because this is telling us it is older emission that, the supernova. Supernova is very recent phenomena. Now, also in the work led by Marco and myself, we published a VLBI census of R299A observations for the first 3 years. We detected almost around 30 sources, most of them Coccola supernovae and supernova remnants, because some of them, were not varying strongly. We did even found evidence for a 1BC supernova based on how fast it evolved. I haven't mentioned this, but let me just phrase it simple. The advantage of using radio observations is that the evolution of these supernovae is much slower than in the optical. So, it is very expensive to observe with VLBI arrays. It's not just, like asking many epochs. So because it's so expensive, we did a monitoring with a cadence of a few months at most, maybe once every few months, every 6 months observations. And this was enough to actually detect the variation of each of these targets. So that's also an advantage. In radio, they are long-lasting events. Well, in short, we found evidence for new supernovae, and this led us to a Coccola supernova rate of at least 0.8 supernova per year for this system. So basically, almost every year you observe, you get something new, a new supernova. We actually detected evidence for what we think, we thought at the time already, it was a flickering microquasar. Okay, let me also, stop here with, saying that all these supernovae, all these VLBI detected supernovae do not get an official recognition. And this is because, of course, it is impossible, going to these dusty buried galaxies and nuclear regions in those galaxies. It is impossible to detect them in the optical, not to mention get a spectrum. So of course there is no official recognition for them, and just as a personal tribute to my wife, so I hope she is happy to have this supernova name as her name, Alicia Supernova. Of course, well, that's for the chuckles. But let me just get to another result. So Rubén Herrera, as part of his PhD thesis, also made this very nice work. He analyzed the radial distribution of supernovae in R299, in the central regions of R299 and R220, also in comparison with the same distribution in M82 and in a sample of normal galaxies. He found what you see in the graph to the right, and the surface density of this radial distribution was in agreement with theoretical expectations. From this, actually, we found evidence that there was a nuclear disk in the central region of R299 and also R220, and that the fact that these agree with these theoretical expectations basically is telling us that this disk is maintained by gas pressure, and that somehow the supernova feedback regulates the accretion of material onto the supermassive black hole here. So that was a very nice result that Rubén published. So let me before we jump now into the second part of the talk, let me just show you in a summary what I have presented so far. That's actually results from the first few years. We see here the innermost HST image with clearly the two gas-rich galaxies that are merging, R299, and the location of the nuclei. Here, the same nuclei, but in radio. This is the VLBI observation. Of course, we cannot resolve the central regions. We cannot see the compact objects that we now know explode. And now we move into the nucleus A. First image with EVN obtained in April 2008. We see a lot of compact sources. What are them? Okay, A0 is what I call also Neff supernova, because Susan Neff in a paper published in 2004-2005, she already mentioned this supernova. In our work, we find evidence for new objects, and what will happen to be this A6 microquasar candidate, because after a number of epochs we detected and not detected the source. It was flickering. You see here also evidence for new targets, new things, which most likely are supernovae, of course. And what I'll discuss in a minute also the discovery of the long-sought AGN A1. Just pay attention to this. And I think in a few seconds we'll start to see, this Taiwan BC supernova, because it appeared in just a couple of epochs, so it was a fast evolving object. Again, the microquasar is back brightening, and in a few seconds you will see a new object which is corresponds to this supernova that I called Alice supernova. I think you want to, because this is a bit maybe too long and I only have 35 to 40 minutes to talk, I think I'll skip the rest of this movie. Okay, let's just go. I think that's the new Corcola supernova. Yes, that's Alice supernova. Okay, so an important thing R299 has been also used as a template, for correcting the missing fraction of Corcola supernovae across the star formation history. So in a paper led by a colleague, friend Seppo Mattila, we combined the near-infrared observations, optical, and the VLBI observations that I just showed to estimate this missing fraction. Well, this is important because the star formation rate across history, a few years ago, was not in agreement with the number of supernovae we were detecting. So there was this mismatch, so the so-called missing fraction. Okay, now we know after this paper especially that there is no surprise. We are simply not detecting any Corcola supernova when we look towards the central regions of these LIRGs. Not because they are not exploding, simply because we cannot detect them using optical in the traditional approach. So VLBI observations have proven to be essential, in combination also with near-infrared observations, by the way, to correct for the missing fraction of Corcola supernovae. Look at the plot to the right shows that we, even at redshift 0 locally, we lose something like we miss something like 20 to even 40% of those supernovae. And we go back to redshift 2, it can be as high as 55%. So 1 out of 2 supernovae is being missed. So correcting for this is really important. And nowadays that JWST observations are actually the James Webb Space Telescope is functional. This is even becoming more important in connecting supernova rates with star formation across the history of the universe. Let me now talk about this glitch in the system. So A1, was it this a supernova remnant or chain of our superstar in a superstar cluster, or was it something else? So let me just recall that in the previous slides I've shown you a number of compact sources. The brightest of all the sources in nucleus A is this so-called A1 source. Initially we only had 5 GHz observations. So we started, of course, the monitoring using them multiple frequencies. I think we convinced the EVN PC that this investment of time and resources was worth the effort. And boom, from these almost contemporaneous observations in June 2009, we detected that this A1 source was not just, it has some connection with this A5. You see here is clearly. Now also notice, by the way, the A0 is not detected. But let's focus on A1 through A5. Basically, we found that A1 had a flat spectrum, typical of AGN. Wow, what a coincidence. That A5 and those components here had a steep spectrum in agreement with expectations from a jet-like structure. Morphologically, this looks very, very much like a core jet. We also, based on other arguments that I don't have the time to explain here, please go to our paper. We could rule out a superstar cluster origin for that. Then comparing the radio luminosity and the X-ray luminosities for this source, we found that it was in agreement with a low luminosity AGN. So basically, all the evidences put together convinced us that we had found the long-sought AGN in R299A. Now, let me now focus on this interesting A0 supernova detected initially by Susan Neff that is not seen, the same time is not seen at lower frequencies. Okay, well, the explanation, the straightforward explanation is that it's not detected simply because we have a foreground H2 region. We are seeing a lot of supernovae here, so we know there are star-forming regions, and an H2 region is the perfect, the simplest actually explanation. So AO has been detected for many years, so it's a long-lasting supernova, and it's so close, it's very close to the AGN. It's just 2 parsecs away. So we think what is happening here is that the low luminosity AGN is, let's say, low luminosity among other things because the supernova feedback is hindering accretion onto the supermassive black hole. It's just hitting the gas so much that it's, the gas is not cooling down efficiently and it cannot fall, let's say, freely onto the supermassive black hole. So it is a low luminosity AGN. So that was the glitch in the system was somehow solved. And now finally, let's move for the remaining part of the talk into the other nucleus B1 or B, which is the host to the deeply hidden supermassive black hole. So B1 is actually heavily obscure. When we compare to nucleus A, this is much more obscure. Actually, it's a quantum thick AGN based on hard X-ray observations. So it has fewer compact objects than in nucleus A, as you can see in the bottom left image. So it has some, supernovae. We are also monitoring that nucleus, but it's about 6 times less prolific than nucleus A. It has an estimated mass of the supermassive black hole of 20 million solar masses. And from infrared observations, it has been determined that the AGN torus, we see the AGN torus edge on. This is important for you. You will become clear in a minute. And the fact is that it is this B1 where we detected a tidal disruption event. So I will tell you now the story. So before this introductory slide is that, for those of you that may not know what is a tidal disruption event, this is the result of a star that is being ripped apart when it passes too close to supermassive black hole. The supermassive black hole rips apart the star, and part of it falls down towards the supermassive black hole. And before it is, eaten by the black hole, it forms an accretion. This can, it has been theorized, like this nice paper by Janios and Metzger, that there would be a TDE launch event. This transient event would be powered by synchrotron radiation emission over a time scale of years, and would eventually decelerate. Okay, so let me now also tell you that back in January 2005, there was an infrared detection of a burst in the nucleus B1. You see the top right image shows the different images of the post and pre-explosion. So clearly there was a strong burst that was immediately followed by my colleague Seppo Mattila and his team. And that was part of a program to search for supernovae in the infrared. Okay, so at that time I didn't even know who was Seppo Mattila. We started collaborating later on. Yeah, let me focus in the talk here. So the infrared properties of these bursts basically are summarized in those two graphs. So to the left, we see that the infrared spectral energy density evolution is well fit by a black body. A black body that cooled down from around 1000 Kelvin to about 700 Kelvin over 4,000 days. And the integrated black body luminosity was huge. So over those 4,000 days, it exceeds 10 to the 52 ergs. This is among the brightest transient events ever found in AGNs. So we were maybe at the time initially, not 4,000 days later, but initially we thought, well, that's an incredibly bright supernova. Okay, we also model this spectral energy distribution using very good, very accurate models developed by our colleague Andreas Estathew. So you see here in the pre and post outburst, the main ingredient that is needed to explain the SED is the so-called polar dust. This is an ingredient that is nowadays has been applied often to model the AGN infrared emission from AGNs. here the important things is that the temperature of this polar dust went up from 500 to 900 pre to post outburst, and this geometrically the covering factor of this polar dust went out very high. This allows us to estimate the radiated energy, which is, you know, a few times 10 to the 52x, in agreement with what I just showed in the previous slide. So, you know, okay, this is telling us it was a very bright event, energetic, but what is it in the end? Okay, so the first anomaly in the system was that, you know, there was no radio emission initially. So we see that based on the modeling of the infrared observations, we estimate that the date of the explosion was on the 22nd of December 2004. Very early in January 2025, there was no radio emission from that site, and only in July 2025 there was a detection of the radio burst coincident with the infrared burst. That was, you know, hinting, okay, we have found a delayed radio emission from this thing. And as you will see in the next slide, this delay, of course, is the time I took the jet from this TDE to break through all this, you know, this absorber. So what you see in the top panels is the 5 GHz observations. The bottom panels are 8.4 GHz or 3.6 centimeters, and we see that this thing developed from being nothing, being then point-like, and eventually, you know, a jet-like structure. Actually, I would say that it's even more. You know, you can see that at the site where, you know, in most cases, if this was a normal AGN, we will have a constant, you know, emission, the core. There is no core. I mean, the thing is being just expanding away. So at the site of the origin, there is nothing a few years later. That's very important. I mean, this is not, let's say, expected for normal AGNs. So, you know, when we model, we started to model the radio emission and the radio evolution of this R299B81 target, and the energetic are consistent with a TDE launch jet. So to the left are the model-like curves along with our observations at different frequencies, and to the right you have the jet, the intrinsic kinetic energy being corrected versus the speed of the jet of the target compared to other events, and also, you know, low luminous AGNs or time 1BC supernovae. So basically it is in the regime of TDEs. It's also in agreement. That's the point. And here, this final slide to convince you that there was a TDE launch jet. So what here I'm showing is the viewing angle of the jet versus the true speed of the jet in units of the speed of light. So the red lines correspond to the limits obtained from our VLBI observations. You know, from this monitoring that I just showed, we were able to estimate the apparent speed of this jet expansion. It was 0.25 plus minus 0.03. So here we are seeing the generous 3 sigma uncertainties. Now the dashed blue line corresponds to the limits from the fact that we didn't detect the counter jet. And finally, from modeling the radio light curves, we obtained the black dot dash lines. In the end, we are left with a small region allowing for this jet. And if you see, you know, it's not only constraining the speed of the true speed of the jet to be in between 0.22 to almost 0.3, but the most important thing is the viewing angle. This is just between 25 and 35 degrees. So this is inconsistent with the fact that we are viewing the AGN torus edge on, because, you know, the standard way this normal AGN is that basically the jet is ejected almost perpendicularly, maybe not necessarily perpendicular, but almost, and we are really far from that. I mean, this is not a normal ejected jet. This is what we think a TDE driven jet, and I think by nowadays everyone accepts that. So, you know, just to summarize, I'm here in this slide. There was a bright burst in the infrared that, thanks to the monitoring of VLBI, where we witnessed that it changed from being point-like to a core jet to a jet-like structure expanding out. We confirmed that this was the first ever resolved radio jet TDE launch radio jet. And as a summary, because I'm coming to the end of the talk, let me mention that the TDE, of course, generated lots of X-ray, UV, and optical emission that we simply didn't see because it was essentially absorbed by the surrounding medium. The dusty torus obscured the direct line of sight to the supermassive black hole, but the polar dust radiated all this emission in the infrared, and then the transient radio emission from the TDE from this jet, was actually what we saw with some delay. Okay, so it is, however, after 18 years, so this is one of the most recent images we have obtained from this thing, because after a few years we say, okay, well, what has happened with this jet? We expected to see it, opening a lateral expansion. No, the jet keeps expanding and decelerated, and too well collimated. So these are two puzzles we need to solve. The fact that there is still no clear evidence for lateral expansion, that there is still no evidence for deceleration, what we should have expected. So there are maybe various explanations, but they are difficult to, I think, to interpret with the fact that for so long the jet has been expanded. But we are now collaborating with theoreticians to actually model this thing. So stay tuned, because this R299B1 81 TDE is still probably giving us more surprises, and the story is not over. Let me also, the next chapter in this saga is the systematic reanalysis of all VLBI data for R299. So to the left, we just see a manual analysis panel with a manual analysis done by a black belt radio VLBI, as shown. And then the bottom panel is the pipeline resulted automatic pipeline from end-to-end calibration and imaging using the VLBI pipeline by Jack Radcliffe, which is also part now of our team. You see the results basically validate the pipeline. Actually, even we get slightly better results, which is, this is very good. I mean, we don't want to waste, our life, reanalyzing dozens. We have so many now epochs that it would be crazy to do this manually. So we want to do this in a more or less automatic way. Of course, supervised by human, but nonetheless automatically. Also, the central panel shows just one image, one epoch from at 6 centimeters using the pipeline. And basically, again, the results are extraordinary. We detect essentially all of the sources we have seen in the stack image that we published in Bondi et al. In 2012. So, the next chapter is actually a massive reanalysis of all existing EVN data for R299. So I think with this, I can summarize the talk. During this almost 40 minutes, I've told you about, the R299 reloaded. We have seen Coccola supernova factories in the nuclei A and B. We have witnessed the detection of the long-sought AGN in nucleus A. We have detected, a TDE in R299B1, and actually the very fact that we detect a TDE also told us where is the AGN, because of course I didn't mention that, but one of the useful things about TDE is that they tell us where the AGN lives. But this, I think this R299 is like this matrix saga. You have matrix 1, then reloaded, then matrix resurrections. It's a never-ending story. So I think stay tuned, and I like to end by thanking the EVN. I think without them, without the support of the EVN, this project wouldn't have been possible. So long live the EVN. It will give you milliard-second target location. It has megawatt-second astrometric capabilities, incredible imaging capabilities, despite one has to fight sometimes with the the reconstruction. We all know the VLBIs, but it's really worth the effort, as I hope you have seen during this talk. And it has ultra high sensitivity qualities. Moreover, nowadays the EVN is probably the only VLBI array that truly guarantees true open access to everyone, unlike some institutions on the other side of the ocean that recently has changed their policies, leaving this less open. And I think I learned with I will paraphrase Morpheus. You take the blue pill, the story ends. You go back to your room and you don't use VLBI. or you stay in VLBI land and the EVN will show you how deep the rabbit hole goes. So thanks a lot for your attention. I want to give a special thanks to all my collaborators and friends that have accompanied me in this matrix revolution. Thank you very much.
Yeah, all right. Thank you very much, Miguel, for such a wonderful talk. We will open the floor for questions, and please keep your questions coming in the Q&A chat. And also, for those watching live on YouTube, you can put your questions using the chat facility on YouTube, and we will attend to them. So there's a question from Sandor. Sandor wants to know if there's any other potential target galaxy with such a rich variety of compact radio sources.
If there is such a galaxy, sorry, could you repeat again?
Yeah, the question is there any other potential target galaxy with such a rich variety of compact radio sources?
Okay, so of course, well, we have also R29, R220, which is a LIRG, but it's farther away. So I guess this is probably the best one can have within 45 megaparsec in the northern hemisphere. There are also, of course, M82 other starbursts, but I think that's the best in terms of LIRG. So.
Yeah. Okay, thank you. We've got a question in the chat. Apologies, I'm not sure I can pronounce the name right, but the question is, how do we know that components A1B and A1C are AGN jet components and not diffuse emission?
Oh, okay. That's a good question. Okay, it's not diffuse emission because the very fact, I mean, one of the limitations or advantages of VLBI is that it is sensitive only to compact radio emission. So the very fact that we detected it at with the VLBI array is telling us that the brightness temperature is so high that it's non-thermal radio emission. Okay, so it's compact, so it is something there. The fact that we didn't detect a 5 GHz, it is due to the fact that to a spectrum, synchrotron radio emission tends to have a steep spectrum. So no, I would say, I mean, it's not diffuse emission. We are detecting the compacting. I mean, we are not inventing this. It's just we are seeing it. I hope this answer. I mean, we can discuss this some later time, but no, that's for sure.
All right, thanks. Yeah, we still have time for some more questions. So if anyone has got more questions, please feel free to put them in the chat. And Benito, are we having anything from YouTube? Okay. Yeah. All right. So I have a quick one, Miguel. Given all the interesting work that has been done on Aptuna 9 by you and your colleagues until now, with the era of SKA looming, what is the expectation? Like, how likely are we to detect some of these things, and in what sort of fraction or percentage wise?
Okay, yeah, that's a good question, and that I didn't touch. So thanks for the question. I think with SKA we will be able to actually do this on let's say a population or demographic scale. So going from not just using R299, but I mean there are also maybe not such a good standards, but there are many others. For example, we have the so-called LIRG sample, and Javier Moldón is leading an effort with his paradigm sample. So these are galaxies that are luminous infrared galaxies, and with the SKA, the combination of sensitivity and resolution will probably, SKA VLBI. I mean, we will need anyway the VLBI long baseline. So that's something, goes without saying. I mean, we aim at tracing the compact radio emission, we need SKA plus VLBI. So SKA will not be enough. I think I've convinced you that long angular resolution has some advantages, but it doesn't locate the compact sources. So we'll need VLBI. So talking about SKA plus VLBI, yes, I mean the future looks promising because we have a number of good samples. I am also aware, we won't go to every and we won't shoot at anything that moves in the sky. We'll have to select, you know, a number of good samples to do this. But yeah, that's something we are starting to be prepared for this. Which are the best targets? Yeah.
All right. Thanks. I think we've got a question from Daniel Pele. The question: at the distance of up to 9, what fraction of supernovae are expected to be detectable with VLBI, and what fraction will be too faint to detect? And can you also independently constrain the core collapse supernovae rate in the galaxy from this survey to compare by the far infrared radio-based estimate?
Okay, I think there are two questions here, right? There are two questions, right? So okay, let me just answer the first one because I understood perfectly the first one. Maybe the second one I need some clarification. So for the first one, okay, I think basically we are only missing in terms of radioluminosity only very peculiar one, like let's say 87A objects, which are really, really peculiar and very rare. So I would say that, I mean, we are sensitive to essentially all kinds of type 2 supernovae. I mean, that's our type 1bc also. And the only limitation is that basically more than the sensitivity, the cadence. For example, a type 1bc supernova could be very fast evolving, maybe a few months. Okay, we can miss it. Okay, that's possible, but you know, the fraction will be very limited. So essentially, I would say that nowadays, especially nowadays, we should be sensitive to essentially all of the core supernovae except peculiar ones like 87A. And then the second question, I think, so is he asking, is Daniel asking about if we can extrapolate this to our galaxy? Is that the question, or?
Okay, so yeah, so okay, Daniel says no, just for up to 9.
So could you then
so the question is, can you independently constrain the core collapse supernovae rate in the galaxy from this survey to compare by the far infrared radio-based estimate?
Oh, okay. Yes. I mean, that's something indeed that's one of the goals. So yes, we one of the things we have been trying to do is actually estimate the core collapse supernova rate from just the VLBI observations, and then compare this with you know, what comes from just converting the far infrared into core collapse supernova rate. So they are in rough agreement, you know, because also, you know, the near infrared observations have estimates have some limitations, but yeah, that's one of the good things. Again, you know, also to guide us, you know, when we go maybe back in Redshift. So yes, we can do this.
Yeah. All right. Thank you. I hope, Daniel, that answers your question. And there's a question from Mark Sargent. Mark says, thanks for the fascinating talk, Miguel. Can you say a bit more about how the missing supernovae fraction and its predicted evolution with redshift was calculated?
Okay. Yeah. That's maybe a question better to be asked to Seppo, because you know I was collaborator but didn't do the actual calculations. But let me see. So basically, we combined near infrared observations for R299 and our VLBI, you know, detected supernovae. So that's we then estimated the fraction that was, you know, basically missed in the optical. If I'm correct, but you know, Seppo Matila, who I hope he's here in the talk, may answer more properly. We could estimate the fraction of this supernovae that was not detected by in the optical, and then was extrapolated to, you know, to different redshifts with a number of assumptions. So I'm not. I think I prefer to not to mention with kind of exact assumptions, because Seppo knows better and I could be wrong. But yeah, Mike, that's a very good question. And okay, if Seppo is around, or even if he's not, I will ask him, and I will go back to Mark. Thanks a lot.
Okay, so hello everyone. I'm actually around, so I will give a brief answer. So basically, we used the work of Miguel and colleagues in the radio to get the radio estimated supernova rates. Then we used the infrared SCDs to estimate based on the star formation rates how many supernovae would be expected, and then we compared with the optical and infrared detections by various surveys over time. And that was basically the ingredients. But please have a look at the paper to get the more complete picture. So thank you.
Yeah, you know, it was in 2012. Sorry, Mark.
All right. Yeah. Thanks both of you. And from Mark says thanks to the both of you. I think we are almost 4 minutes to the hour. There's no more questions in the chat or the Q&A. Benito, anything from YouTube? Okay. Well, then on that note, we will thank Miguel again for such a wonderful talk. And before we sign off, we have a couple of announcements, and I'll hand over to Benito to give us those announcements.
Yeah, thank you very much. So I only have one quick announcement. We already have set the next EVN seminar that will be done by Sándor Frey from Hungary. And he will talk about VLBI and Gaia astrometry on the service of AGN Astrophysics. And that will be on Friday, 5th of December. And with that, we will conclude this year, and then we will continue the beginning of next year. And the last maybe quick announcements is that the EVN Symposium and Users Meeting will take place next year in Manchester in September. There haven't been any official announcement yet, but then you can start holding your date for that. I'm not sure if Emmanuel has already the final date for it, but then it will be in September in 26. So ping it in your calendars.
Yes, thank you very much, Benito, for mentioning that. We are preparing to make first announcement for this. Yes, it will be in Manchester, like Benito said, and the dates are fixed. The dates are 14th to the 18th of September 2026. And if you look on CADC, the Canadian Astronomy Data Center Service, you will find the event listed on the website. So yes, first announcement will be made very soon, and the details about registration, abstract submission, and everything will be out. And yeah, so please put that in your calendar, 14th to the 18th of September 2026.
It will be a good occasion to meet all of you there in person and online, and see all the science with the EVN. So with that, we can conclude here. Thank you, everyone, for joining the seminar. Thank you, Miguel. It has been a great talk, and Emmanuel and Anya for the introduction of the seminars. See you in December.
Yep.